Greetings to everyone. My name is Mohammad Noman Tariq and I have done my electrical engineering from Sakhar IBA University. Today I will demonstrate my final year project along with my groupmate engineer Afzal Ali. We have done our project under the supervision of a well-known personality Dr. Fahim Akhtar Chachak. Our project is co-supervised by engineer Mahmood Mughal. The title of our project is Multiport DC to DC converter which is capable of transforming variable or fixed DC inputs into fixed DC outputs of our desired values. The input sources could be photovoltaic cells, fuel cells, wind turbines, or batteries. From dedicated outputs like 5 volts, 12 volts, and 24 volts. From 5 volts, we can charge electronic devices like mobile phones, laptops, earphones, etc. From 12 volt output, we can run our home appliances like 12 volt DC fans, 12 volt DC lights, and we can also charge our batteries of 12 volts. From 24 volts, we can run DC pumps. Also, we can exchange energy between houses using 24 volts output. So, moving forward, we will follow problem statement, literature review, what is our proposed solution, aims and objectives of our project, methodology, future recommendations, and references. So in problem statement, we have seen many projects involving AC and DC at the same time. If we talk about DC microgrids and if we involve AC counterparts in DC microgrids, the efficiency of DC microgrids reduced up to 13% due to their AC counterparts. So that's why we only prefer DC. DC appliances are more efficient than AC appliances, but we are not shifting towards DC appliances which are coming from renewable energy resources and distribution generation due to integration problems of multiple variable sources. Mutual induction based topologies reduce the power during conversion due to losses. One of the main reasons behind electricity in our country is expensive electricity, but still we are not shifting towards renewable generation. As far as literature review is concerned, single input, single output converters circuitry is less complex, it takes less costs to build CISO, but multiple input and multiple output converters are more reliable than single input, single output converters. If we talk about comparison between this DC and AC, AC has losses due to inductive and capacitive effects during transmission. But in DC, these losses are negligible. The investment cost in AC, such as to build a hydropower plant or to build other power plants which produce AC, it takes much cost, but for DC, investment cost is reduced. The efficiency of DC is very much higher as compared to AC. If we talk about the power quality, we face power factor problems and other problems like inductive effects, capacitive effects in AC. But in DC, we do not face these problems. If we talk about the present trends, DC loads are more efficient, DC generation is easy, and we can produce DC by using PV modules, which is a renewable energy. We can store DC. Also, there is a DC microgrid, a concept in which distribution generation can be used to fulfill the demands of electricity. So, our proposed solution is to design a multi-port DC to DC converter, which is also a multiple input, multiple output converter in Matlab, and then its hardware prototype. Here is shown the block diagram of our project. We can take Solar panel outputs wind turbine, which is of course distributed wind turbine, which gives us DC instead of AC by commutation or rectification. We can also use battery, which is fixed DC source, also fuel cells. If we take AC from grid stations, we would definitely rectify it and then give it to our multiport DC to DC converter. At output, it gives fixed output voltages like 12 volts, 5 volts, and 24 volts. We can connect our home appliances to the output of our converter. Our aim is to design and analyze prototype of multiple input, multiple output DC to DC converter. The objectives of our project is modeling of MIMO DC to DC converter and its control in Matlab, its hardware implementation, and then behavior analysis of MIMO converter at different inputs and outputs. We have followed the methodology in this project, which is mathematical modeling of our converter, its simulation in Matlab software, and then hardware implementation. After software and hardware implementation, we will move towards the behavior analysis of our converter and then write thesis. So what is a buck boost converter? Basically, we have used 3 buck boost converters to attain 3 different output values. A buck boost converter is capable of increasing output from the input or decreasing the output from input, depends on the input value and the duty cycle we give. In our case, the buck boost converter will operate in CCM mode. In CCM mode, the inductor current will never approaches to zero. Gate pulse determines for how much time MOSFET allows input to flow through it. It is controlled by duty cycle. Inductor charges and then discharges to produce output. During inductor charging, the diode is turned off and capacitor is supplying current to the load. When the inductor is charged, the duty cycle gets zero and inductor starts discharging. During inductor discharging, the current flows and charge the capacitor. Also, it gives current to the output load. The formulas are shown in the next slides. So,
now we are moving towards mathematical modeling. We are using 8 mega 328 microcontroller. The property of 328 the property of 8 mega 328 microcontroller is it can sense only 5 volts. Although our input value is up to 20 volts. So we have used VDR circuitry to sense more than 20 volts. The voltage drop across R2 resistor is sensed by the microcontroller and we get output from digital pins of microcontroller which will send the relay. Now we have calculated inductor values for buck boost and capacitor values of buck boost by using buck boost formulas. We have set voltage ripples up to 1% of output values and current ripples 5% of inductor values. And this is our duty cycle formula, V out upon V in plus V out. And this is our inductor formula according to buck boost formulas. This is capacitor formula and we have selected these values. And this is for 12 volt output. We have set same as according to 5 volt, 1% of original value, and we have set it current ripple 5% of inductor value, and as according to this we have still calculated duty cycle, inductor, capacitor value. Now these red shaded areas are the values which we have calculated for our hardware implementation and software implementation. These values are according to our choice because the problem we face, inductor and capacitor values are not available in our market. So we have set values according to which values are available in our labs and in our department and in our markets. So this is for 5 volt calculation. These calculations are for 12 volt. These calculations are for 24 volt. This is a software implementation. This software implementation is for fixed inputs and fixed duty cycle. We cannot change duty cycle in this. We have set fixed input and fixed duty cycle, and we have get 5 volt, 12 volt, 24 volt fixed output. But this is not our requirement. This is the analysis of fixed input software implementation in which load current is stabilized after this time, and in this it takes this time, and we have see that load voltages.
So if we come towards implementation of MIMO converter using variable DC inputs, here we can see there is a source. We did not define 12 volts or 15 volts here. Instead, we have defined V base, a variable at the place. The reason behind this is different we need different duty cycles here. When the input is changed, there would be a different duty cycle. So in order to change the duty cycle as well with the input, we give a variable instead of a fixed value, and then we use the formula of duty cycle in the place of duty cycle. So if we give 5 volt here, we will get 11 volts, which is closer 11.03, which is closer to 12 volts, or 4.18, which is closest to 5 volts, or 23.15 volts at the output. So we keep changing the inputs and see that the output voltages remains constant. Here is the behavior analysis of our output at 5 volt inputs. We can see that the output is stabilizing itself at the desired value, which is 12 volts, after 0.3 seconds. For the 5 volt output, we can see that it is stabilizing itself at 0.2 seconds, and similarly for the 24 volts output, we can see that it is stabilizing itself before 0.2 seconds. Moving forward, we also have done behavior analysis at 10 volt input. We change the input from 5 volt to 10 volts and see that the output is stabilizing itself after 0.1 seconds or 10 milliseconds. At the 15 volts, if we change the voltages from 10 to 15 volts, we see that again we are getting 12 volts, 5 volts, or 24 volts, and it is also stabilizing its outputs in less than 0.1 seconds, which means that if the input is closest to the output, the ripples will get rectified, will be neglected or get out from the output in less time. So coming towards the cost analysis, our circuit has been designed in almost 2500 pkr. We have used MOSFET IRF 5B4111115. We have chosen this MOSFET because we need the switching frequency of up to 30,000 Hertz, and the duty cycle which will be given to the MOSFET will be of 5 volt. So that's why the reasons we have used these MOSFETs in our buck-boost circuitry. We have used diodes IN4148, which is a Schottky diode in our circuit. We have used the relay because we need switching whenever, if we are giving the input from PV, the relay 1 will be conducting. If we if we give input from uh, wind instead of PV, relay 2 will be get active. And if we uh, give input at the dedicated third input, it could be battery or any other DC source, the relay 3 will get active and other two relays will not get active. This is a 4 channel relay. We have used ATmega 328P for sensing the input as well as producing three different duty cycles for buck boost circuitries and a digital signal for actuating the relay. Relay also needs VCC of 5 volts and ground, which we have given it from ATmega 328P pins. We used resistors as loads of different values. We also used capacitors according to the mathematical modeling, also the inductors. We have used capacitors which are available in market by combining them in series or parallel manner to get the desired capacitors value. As far as inductors are concerned, we use toroid material and make our own inductors of desired values. After that, we have done PCB fabrication. We have designed our PCB on Eagle software. Crystal oscillators are used with ATmega 328P IC, also headers. So this is the PCB schematic of our project. We will demonstrate the hardware hardware part of our project. So firstly, coming towards the components, this is our ATmega 328 microcontroller, which is also used in Arduino Uno. These are the analog pins. After that, we have digital pins. We also use some PWM pins in our project. These are defined here. So firstly, coming towards this is VDR circuitry, and these are the input part of our project. First three pins are our input pins and the fourth one is ground. We have connected 4x2 pin here because firstly our input come towards the input part of our project, and then it will move towards the VDR part. The voltage across second circuitry will be sensed by A0 analog pin, A1 pin and A2 pin. It depends upon which input is coming. Input 1, input 2 or input 3. A0 pin senses the input of A1, input 1. A1 pin senses the input 2 and A2 pin senses the input 3 and tell the microcontroller. From here, one wire goes towards the relay. We have used 4 channel relay and we have utilized its 3 channels in our project. So after sensing the input, it will generate digital signals, and these digital signals actuate the relay. It may be relay 1, relay 2 or relay 3 depending on the input signal, and also it generates duty cycles which will move towards the gate terminal of our MOSFET. When the relay is switched on, the relay output goes towards the input of our MOSFET circuitry, this is our Buck-Boost converter circuitry. The first one is MOSFET. After that, we have used pins for pins because we have to set here the inductor, and we have designed inductor at our own. That's why here we have used headers for MOSFET circuitry 1, MOSFET circuitry 2 and MOSFET circuit 3. After that, these 3 are Schottky diodes and the capacitors are connected in parallel to get the desired value. From here, we will get our output voltages. All of this circuitry is required by the 80 mega 328 for its working. This is AVR IC. This is for FTDI cable. It is used for boot loading, also for the program burning. So after that, we move towards the PCB board. So after routing, we will get this type of PCB board. We route it so that we can get a very small circuit, so that overall size of our project decrease. These are the hardware results of our converter. Here we can see that we have given 8 volts, 10 volts and 12 volts or 5 volts, and we are getting the same results: 5 volts, 24 volts. So coming toward the problems we faced while hardware implementation, we need capacitors and inductors of values which are not available in our country. So as far as capacitors are concerned, we have combined capacitors in series and parallel to get the desired value of capacitor. In case of inductors, we design our own inductors using toroid material. Another problem is that our input voltages are greater than 5, and 80 mega 328P microcontroller can sense up to 5 volts. So we divide these voltages using VDR and use two resistors. The voltage across the second resistor will be sensed by the microcontroller. In case of 20 volts, only 4.7 volts will be appeared on the analog pin of microcontroller, and then we multiply it with the certain factor we are getting from the formula of VDR to get the original voltages using coding. In future recommendations, we recommend DC net metering so that we complete the concept of DC microgrid and use this converter in this microgrid. Another 48 volt output can also be get by fabricating another buck boost converter circuitry. From 48 volts, we can exchange energy at longer distances than the 24 volt output. We can also make our converter smart. Then it will tell us how much energy we are getting from the input and how much we are utilizing at the output, so that the remaining energy can be stored or it can be transferred in the network. So these are the references we used in our project. We take help from these references